So we're now doing chapter 11. We're going to do lesson 11.1, permutations and combinations. So we're going to solve problems using what's called the fundamental counting principle. And basically that tree diagram we were doing, okay, that uses the fundamental counting principle. And then we're going to solve problems involving permutations and combinations. And they're very similar, permutations and combinations, but there's one thing that's different about them that we'll talk about. Okay? So we've used the fundamental counting principle when we've done tree diagrams. And the only thing that happens there is that if we have multiple things, we multiply them together. Okay? So for instance, on this tree diagram we had here, that in this problem was that we have 3 different choices here times 3 different choices there. And 3 times 3 is 9. Okay? It's as simple as that. So first of all, we're going to use the fundamental counting principle to answer some questions. So here it says, to make a yogurt parfait, you choose 1 flavor of yogurt, 1 fruit topping, and 1 nut topping. How many parfait choices are there? Okay. And this is where we're going to use the fundamental counting principle, which says that however many of each you have, you just multiply them together. So how many choices do we have for the flavor? 2. And for our fruit? Okay, 5 fruits. And how many nuts? 3. And then we just multiply them together. So there are 30 different ways to make a parfait. Another one of those problems, I wish they were all like that, right? Okay. Now, some of the counting principle problems are a little bit different. Okay. Like here we have one consisting of passwords. Now, how many of you guys have passwords? Okay. How many of you have multiple passwords? Okay. How many of you have 5 or more? Wow. Okay. All right. That's probably close to what I have to remember. Let's see. I've got, on my laptop, I have my login here, a login at school, which is different. Okay. So that's 2 of them. I have, let's see, 1 for Facebook, 1 for, most of my stuff I use the same password, but then on our bank accounts, we have 2 different bank accounts. They have different passwords. And usually my wife uses pretty close to the same one most of the time. So, but then you have those places that say, well, your password has to have a capital letter and a symbol. Well, I don't normally use capital letters or symbols, and I use numbers and letters. But so there can be so many different passwords, and we could actually figure out how many there are. And the nice thing about it is that there's so many different ones that it would be very difficult for somebody to break in. Okay, of course. We've all had passwords stolen probably, right? Anybody not had a password or you get your Facebook get nailed by somebody? Okay. All right, I have, and it's really frustrating when that happens. Okay. All right, so here it says a password for a site consists of 4 digits followed by 2 letters. Now the thing is here is that we have to make a differential between digits and letters because obviously those things are different. So what I do is that how many different characters do we need altogether? 6. So I'm going to put 6 lines here to represent the 6 different characters. Okay. Now it says the letters A and Z are not used, and each digit or letter may be used more than once. Okay. So the first 4 are digits. And how many digits do we have? Okay. Is 0 a digit? Yes, it is. Okay. And so we have 0 through 9, which is 10. So there are 10 digits. So I have 10 different possibilities for each of these spots here because it says we can use them more than once. Okay. So I could have 5, 5, 5, 5 if I wanted. Okay. Now it's followed by 2 letters, and it says A and Z are not used. So how many letters are there if we don't use A and Z? 24. Okay, so we have 24 here, 24 here. Okay. And this is a fundamental counting principle problem, and all we do then is multiply them. So we get 10 to the fourth power times, what's 24 times 24? Anybody know? Top of your head? Okay, it's 576, right? Okay, you knew that, didn't you, Matt? All right, so then we just multiply them together, so we got 4 zeros in, right? So 5,760,000 passwords. Now think about it. That's just if we have 4 digits and then two letters. Okay. And that doesn't even take into account the fact that we could have capital letters and lowercase letters, does it? Okay. All right. So that's why it's so hard, you know, for people to be able to steal your passwords unless they really know something about you where they can kind of guess what you might use. So, okay. Okay, a permutation is a selection of a group of objects in which order is important. Okay, so we're going to talk about permutation now, and then we're going to talk about a combination. Permutation, order matters, or order is important. With a combination, order does not matter. And so the difference between them gets a little tricky sometimes. But here, order matters. So I have one permutation be the letter A. If I had the letters A and B, then I would have 2 permutations. I have 2 choices for the first letter and 1 choice for the second letter. And the thing is that things cannot repeat either. Okay? So like the previous problems, we said we could have the same letter over and over again. In this case, you can't. It can only happen once. If I had 3 letters, A, B, and C, then there are 6 different permutations for A, B, and C. Okay? So we have 3 choices for the first letter, you know, A, B, or C, and then you would have 2 choices for the next one, and then 1 choice for the last one. And so with permutations, we're going to look at a couple different things. One is something called a factorial. Okay, the factorial of a number is the product of all the natural numbers from that one to the ones below it. So if I said 6 factorial, it would be 6 times 5 times 4 times 3 times 2 times 1. In our warm-up, we had 7 factorial, didn't we? We had 5 factorial, and then we had 7 factorial. Okay, all right. Okay. This was 5 factorial, because it starts at 5 and multiplies all the numbers down to 1. And this was 7 factorial, because it started at 7 and went down to 1. So you can look at, like number 4 has 7 factorial divided by 4 factorial. And those are helping us with what we're going to be doing. Okay. Sometimes you may not want to order an entire set of items, though. Okay. So we're using factorials when we have a whole set we're doing. So if I have 10 books and I want to order them, okay, then it would be 10 factorial. But sometimes you don't want 10 books or all 10 of them. Maybe we only want 3 of the 10. Okay. So suppose that you want to select and order 3 people from a group of 7. One way to find the possible permutations is use the fundamental counting principle. So the first person, we would have 7 choices for that person, and then 6 choices for the next person, and then 5 for the next person. And then we can just multiply those together. Well, what that turns out to be is that it's an arrangement of 7 people divided by an arrangement of 4 people. In other words, this is, there we go, my smiling face. That in the numerator here we have all of the possibilities, and in the denominator we have the possibilities that we don't want. Okay? And that still gives us that 210, okay? Which is something we found in the warm-up too, wasn't it? Okay? So we have then the formula for finding permutations. All right? And so we're going to use this formula here, okay, to find permutations. So it says the number of permutations of m items taken r at a time. So in the numerator, we have n factorial. In the denominator, we have n minus r factorial. So in this problem we just did, we would have, it says I have 7 items, and I'm taking 3 of them at a time. Okay? So 7, choose 3. It's a permutation of 7 items where I'm going to choose 3 of them. Okay? So we always put the number of items first, before the P, and then the number of items you're choosing after the P. Or there's another symbols that you could use. You could actually do parentheses. This is a permutation of 7, choose 3. Sometimes you'll see it written that way. Or sometimes they'll write it like this with a little 7 up there and a little 3 down here. Okay? But I would use it either this way here or this one here. Either one is fine with me. So we're going to talk about this 2 different ways. Using the formula, because we need the formula when we get to combinations, so we're going to actually use the formula here. So it says, how many ways can a student government select a president, vice president, secretary, and treasurer from a group of 6 people? Now overall, this is really pretty easy, because here I've got 6 people, and I'm choosing 4 of them, right? Okay. Now, order is important here because I'm actually giving them a title. One person is president, one person is vice president, one person is secretary, one person is treasurer. So order matters. And since order matters, it's a permutation. Well, we could do it this way. I have 6 people to choose for my president. Well, once I chose one person for the president, can he be the vice president? No. So now I have just 5 people for the vice president. Then I'll have how many people left for secretary? 4. And then for treasurer, 3. And so I can use the fundamental accounting principle there and just multiply them together and get the fact that there are 360 different ways to choose a president, vice president, secretary, and treasurer from a group of 6 people. Now, if we use our formula for permutations then, here we have a permutation of 6 people, and we're choosing 4 of them. So in the numerator, we will have 6 factorial. In the denominator, we'll have 6 minus 4 factorial. So then I can do 6 times 5 times 4 times 3 times 2 times 1 in the numerator. And what's 6 minus 4? 2. So then 2 times 1 in the denominator. And so these end up, these cancel, and there we have our 6 times 5 times 4 times 3. And so I could have done it either way and gotten. Okay. Now, that's fine doing it this way as far as using the fundamental accounting principle. But if you have a very large group of numbers, then you would have to write out an awful lot, and that's when the formula is much easier then. Okay. So here, letter B, it says, how many ways can a stylist arrange 5 of 8 vases from left to right in a store display? So we're looking at, here's our keywords right here is from left to right. And that means that order is important, or order matters. Okay? Because of the left to right, order matters. Which that means it's a permutation. Because when we get to combinations, order doesn't matter, so you have to know the difference. Okay? So here now, then, I'm going to use the formula. Okay? So I have 8 items, and I'm going to choose 5 of them. So we have 8 factorial in the numerator, and 8 minus 5 factorial in the denominator. Okay. So here's one of the things I'm going to show you then is that the work we are doing in the warm-up, okay, here's why that work is important, because now I'm going to show you a shortcut here. Okay. That I can stop and write the rest of this as 3 factorial, right? Because all it is 3, 2, 1 that I'm multiplying together. So I can just leave that as 3 factorial. My denominator then is 3 times 2 times 1, which is 3 factorial. And that allows me then just to cancel them out, which will simplify a little bit of my multiplication. And then we just multiply those 5 numbers together. Let's see. Can I do that in my head? Can you? Let's see. 40, let's see. 40 times 42 is 1680, right? 40 times 40 is 1600, isn't it? Okay, so 40 times 42 would be 1680, right? So we have 1680 times 4. Oh, that becomes a little bit more difficult. Okay, let's see, 32, 27, so 0, 2, 7, and what? Okay, 6,720. All right. So that's how many different ways that this person could arrange those vases. Okay, that is a lot. All right. So they should never, if they arrange them 10 times a year, nobody should ever know there's a difference, right? Okay. All right. Now, combinations are very similar to permutations, except the key to these is that order does not matter. Okay? And since order does not matter, this permutation here we have of the 3 letters A, B, and C provided 6 permutations where it's only 1 combination. Because it doesn't matter whether I put A, B, or C first. As long as the letters A, B, and C are being used, there's only one way to do that as far as a combination. A permutation that's 6 different, because order matters. A combination, there would only be 1 different. Okay? So to find the number of combinations, the formula for permutations can be modified. So here's our permutations model here. Ways to arrange all items divided by ways to arrange the items not selected. To where if I want a combination, we have ways to arrange all items divided by both the ways to arrange the items times the ways that not arrange the items, or the ones not selected. And so that produces this formula here for combinations. So you can tell it looks exactly like the permutation one, except we've got n factorial in the numerator, n minus r factorial in the denominator, but then we're going to multiply it by r factorial. So the number of items in the numerator, in the denominator we have the items not selected times the items selected in factorials. Okay. So we're going to use a permutation if order matters. Use a combination if order does not matter. Okay. And here's the thing. So the problem that some students have is determining whether order matters or not. Okay. If they're put in a row or given a specific title, that would be a permutation because order matters there. If I just selected 4 students, that would be a combination because I'm not saying I'm going to do this with them. Okay. Example might be a basketball team. All right. So on a basketball team, a coach assigns jobs to people. Okay. Like there could be lots of times they just give them numbers 1 through 5. Okay. You're the 1, you're the 2, you're the 3, you're the 4, you're the 5, and the players know what they're doing according to that. So if I had my basketball team and I sent them out on the court and I said, okay, Justin, you're the 1, and Logan's the 2, and Ridge, you're the 3, and Travis is the 4, and Matt, you're the 5, okay? Then that would be, order would be involved in that. But if I just said, okay, you 5 guys, you go play, all right? There's no order to that. There's just them going out there. And so that would be a combination. Okay? All right, so there's the difference, all right? Order, specific title, specific jobs, putting a line, something like that, okay? A combination, you're just choosing them. Okay? So example 3, there are 12 different colored cubes in a bag. How many ways can Randall draw a set of 4 cubes from the bag? Okay. Does it mention any order about how he's going to take those 4 cubes? No. Okay. So order does not matter. So that means this is a combination. So my formula is I have a combination of 12, choose 4. So I'm going to have in the numerator 12 factorial. In the denominator, I'm going to have 4 factorial times 12 minus 4 factorial. And so when it's a combination, okay, this is the way it always works. 12 factorial in the numerator, and then 4 factorial, 8 factorial. So these two numbers have always got to add up to what's in the numerator. Okay? And so you could go from here to here. So we do the work, and now here's the thing. I can go 12, 11, 10, 9, and then 8 factorial. Okay, I don't have to go 12 to 1. And then in the denominator, I can do 4, 3, 2, 1 times 8 factorial. Okay, that way makes it easier. Cross these out. Let's see, what's 4 times 3? 12. Okay, so 4 times 3 is 12. And so now I have 10 times 9 times 11 divided by 2. Or I could say this is a 1 and this is a 5. Maybe it's a 5. All right, there we go. Nope, it's not a 5. There we go, 1 and 5. Okay. So let's see, 55 times 9 is 495. Okay. So there are 495 different ways that Randall could just pull 4 cubes out of the bag. Yeah, that would be an amazing job. All right, so let's look at these 3, 6, 7, and 8. And I want you just to look at them. Okay. All right, so number 6. Melissa, what is it? It's a permutation. Okay. Okay. And the reason it's a permutation is because right here it says first, second, and third prize can be awarded. Okay. Okay. Number 7, Derek. Combination. It says how many ways can he choose 4 students to go to the library on the first day? Now it says the first day, but that doesn't have anything to do with the students, does it? Okay. It just says we're choosing 4 students, so that would be a combination. Okay. And how about number 8 then? Ryan? It's a combination also, yep. All right. Gregory has a coupon for $1 off the purchase of 3 boxes of Munchie brand cereal. Store has 5 different varieties of Munchie brand cereal. How many ways can Gregory choose 3 boxes? Okay, so he's just choosing 3 boxes. Yes, Travis.
It's going to be a combination if it's asking for different varieties.
Well, the store has 5 different varieties of cereal. Okay, And how many ways can Gregory choose 3 boxes of cereal? Okay, so that each box is a different variety.
Because variety doesn't necessarily need to be in order, just three different boxes.
Right. Okay. Right. You're just choosing 3 different ones out of the 5 different ones. Okay. So if I chose 3 from these 5, they would have to be different. Okay, does that make sense? Okay. Because these 5 are all different varieties anyways. So if I pick 3 boxes from there, so there's A, B, C, D, and E. If I choose 3 of them, they're all going to be different anyway. Okay, that's automatically going to happen. It's a good question, though. Okay. All right.